Okay, I'm using a text that's from my Colin course just to show you a couple of things that I couldn't quite find in your text. Um, so the first thing is when we're looking at correlation, we're looking at two different, hopefully you figured this out by now, but we're looking at two different variables that may or may not be related. And even if they are related, it may not be linear. So you've learned in the past that, for example, if you throw a ball on planet Earth or anywhere with gravity, then you have this quadratic relationship between the time and the position of the object, above the ground. So those are very strongly related. It will follow the parabola, but they do not have a linear relationship. So the question is to decide if something should be modeled by a line if you're going to try to write it out as a function. So generally, the explanatory variable is the one on the x-axis, the response, the one that you're predicting, is the y. So if you, for example, were plotting height versus weight, then you would assume that you're being given a height and asked to predict the weight. You can do it the other direction just by plugging in, but the expectation is that you're using whatever's on the x-axis to try to predict what's on the y. Okay, so two things are positively associated if generally as one goes up, the other one goes up as well. Generally, as height goes up, weight goes up, especially in the same person, right? Like as you're growing over time. Then a negatively associated pair is things where when one goes up, the other goes down. So when, say, gas mileage goes up, then the amount you spend on gas goes down because you're getting more distance for the same amount, the same gallons. So those are negatively associated. Increase in one, decrease in the other. This is a positively associated plot. This is a negatively associated plot. This one is very strongly associated, but in a quadratic manner. So this is not linear. You would not want to use the correlation or a regression line to approximate on this one. You would want to model it with quadratic. This one's cubic. Again, very strongly related, but not linear. This one, this is just like a blob. It's not, you can't predict one from the other. So on this x, the y's range like this. On this x, same range. This x, same range. Knowing the x has no bearing whatsoever on the y, so they have no relation. So I think the next page has the thing I wanted you to see. Nope. Oh, by the way, the correlation coefficient, it's really this. So really what you do is you take each of the x's and put them in standard units so that it's a list of how far above the mean you are relative to your standard deviation, so standard units. Same thing with y, and you come up with products for the pairs. Then you kind of average those. So this is another thing where we're multiplying by the n minus 1 just to control for the size of our sample. And the bigger our sample, the closer that gets to a true average, just like before. So the result of that is if things that are above the mean are typically paired with things which are above the mean, then those products tend to be positive. And in that case, somebody below the mean would likely be partnered with someone below the mean. So those two negatives would also make a positive. So you end up with mostly positive things that you're averaging. If, on the other hand, when you're generally above the mean, you tend to partner with someone below the mean and vice versa, then your products all tend to be negative. So you are averaging things which are mostly negative. So I guess this wasn't the page that had the thing. This doesn't hurt to see. I don't know if this is in your text or not, but correlation coefficient is always between -1 and 1. There's no way for it to be anything different from that. If it's -1, that means the two variables are actually on a line, and it's a negative slope. If it's equal to 1, then they're on a line and it's a positive slope. The closer r is to 1, the stronger the positive association, and the closer to -1, the stronger the negative association. Oops, this thing scrolls so fast. If I just, sweep on my mouse. So if r is close to 0, then you don't have a linear relation, and you can't say they're not related, and you can't say you can't predict one from the other. It's just that it's not linear. That's all you really know. Correlation coefficient is unitless, because remember that we put everything into terms of standard units. So at any rate, you get rid of anything like inches or feet or miles, because everything's just standardized to the normal curve. It is not resistant. Things which don't follow the overall pattern could really affect the linear association. Okay, so this has a perfect linear correlation. These are on a line, and it's positive slope, so r is 1. That's one of the easy ones. Same thing here with the -1. It's on the line. Something that looks like this, if I put a line through here, my error is not going to be very high. Everything's pretty close. That guy's the only one that's even really off by much at all. So this has a very strong relationship, which is 0.9. Here's a -0.9. See, it's still very, very linear. You might be called upon to recognize, just by looking, an approximate value for r. So you need to see these and have an idea. And this is a moderate positive relation, although I believe your text, this is one of those things that isn't consensus amongst all statisticians. I believe your book begins moderate at 0.5. And so if you have a 0.4, I think you need to say that it's weak. So 0.4, -0.4, you can still see it's linear-ish, right? You've just got these kind of scattered out guys. This one, again, knowing the x value gives you no help on predicting the y value. It's just everywhere. So it's something close to 0. R is almost never actually 0, but very close to 0. This one also is going to be close to 0, and not because they're not related. It's very strongly related, but it's because it's quadratic. If I tried to use a line in any direction, it's going to be way off, right? So it's still close to 0. It's just quadratic. Let's see if there's anything else in this text that we should... Oops. Okay, so this is making an argument similar to what I was saying before. So these guys, these are going to be a positive times a positive. And these are going to be a negative times a negative. So anything in quadrants 1 and 3 is going to be positive products. And those, therefore, contribute to a positive correlation. This is the only one that's going to be negative. These two are negative. So the question as to whether it's close to 0 is if there's enough junk in these two to offset these two, or vice versa. If they're mostly in these two quadrants, it's going to be positive. If they're mostly in these two quadrants, it'll be negative. Okay, so this is the kind of real way to do it. This that I've been leaving over here, this is the formula you're going to be asked to use. This is algebraically equivalent. There are a bunch of different kind of equivalent methods people have come up with. Mind you, your calculator will give you R, and so will RStudio, but you have to be able to use this formula for the problem sets and the exams for the handwritten portion. Okay, correlation matrix. Excel provides a correlation matrix, which is not what we're going to use, but it's in the R part. So the correlation matrix gives, for every pair of columns, it gives the correlation in the bottom triangle of the matrix. So I'm seeing if there's an example here of an outlier, so that's what I'm looking for. Correlation and causation, I actually did post a link on the front page of third year mathematics, the one that has the little comic strip about how correlation is not causation, links to some things which are correlated, which certainly should not be causation. Yeah, so I guess it doesn't have an example of an outlier, so we may have to come up with one. So this is like a general introduction so far. So let's consider, what if you were asked to calculate R for a set of variables, and what if you were just trying to think about what should R be, okay? So let's suppose, I'm going to try drawing, we'll see how it goes. This is just like situational stuff. So suppose that you have a bottle of water, and you're going to pour it into a glass, trying to make the glass big enough that it can hold all the water. So if I consider the amount of water in the bottle as one quantity and the amount of water in the glass, which right now I guess is just a little, what should their relationship be? So as this one goes down, so that's gone down to there, and it's come in here, so that's more, right? Goes down a little more, up a little more. So every time I have less volume here, I'm going to have more volume here, and it's going to be actually perfectly linear unless I like spill some, right? As long as I pour directly into the glass, exactly how much leaves here goes down there. So this is going to be an example where originally all the volume is there, and then as it goes down here, down on this one means up on this one, the same amount. So I'm always going kind of like this as I pour. So I actually have a line, right? So this is going to have R equal to 1 if you don't spill. And it's going to be, -1, exactly -1. If you have something like height versus weight, then each pair is the height and weight of a single person. So there are very tall, skinny people, right? And there are very short, fat people. And there are a whole lot of kind of average people. So most people are in this category, the average people. So it's not a perfect line, but generally speaking, on the whole, as one goes up, the other goes up. So we have a bunch of people who are kind of average. And we do have this tall, skinny guy, right? But since he's tall, even being skinny, he's still kind of with these average people. And then we have this one short, really fat person. So we kind of end up with something like this. It's still linear. They do increase our error though, right? So our R is going to be a little bit less than if we did not have those people. So if you took, instead of just all people, you took, say, all of the Olympic gymnasts, then you'd have a lot better line. So that's an issue of choosing a category that matches. And when you're doing a survey, you don't generally want to choose that because you want to have a better representation of the population. I'm going to take a moment to save this so it doesn't disappear. Okay, I'm going to give some R's and some situations, and they're not going to be perfect because I'm making them up as I go, but I want you to pause the video when they're all up there and see if you can figure out which one is which. Okay, so I'm going to try to make something that has an R of, say, 0.9, an R of 0.65, R of 0, negative 0.4. So this is approximately 0, nearby 0. Okay, I'm going to try. So we'll see what I can come up with. So one of the options will be favorite number, H. One of these things will be height, weight. One of these things will be IQ test at 18, IQ test at 30. So this is age, same person. One of these things will be number of cigarettes per day and life expectancy. And one of these things will be I guess I'll just say the gas mileage, which is, by the way, miles per gallon. That's what that means. Miles per gallon. And money spent on gas. That's probably going to be the least accurate one there, but anyway. So pause this before I finish this sentence so that we can talk about it after you think about it. So write down your guesses. I'm not going to take the time to put it into one of those little quizzy things, but write down your guess and pause. Okay, so the first thing is you could just ask yourself which of these things is most strongly correlated. I'm going to say the IQ is the most strongly correlated. It may be a bit better than 0.9, but it may not. Because the deal is that, first of all, on any given day, there's an error on your IQ. So if you take an IQ test, it's that number, give or take, a standard deviation on IQ, which is not the whole 15. It's a standard error on a given person. So it's different, but there is an error on it. So it's the most strongly correlated, so 0.9 by process of elimination. And that may be fairly accurate because the other thing is that sometimes your brain keeps changing until you're 25. So between 18 and 25, you may actually become a better learner. And IQ measures kind of your ability to learn. And also, people get brain damage, do drugs, drink, and they decrease their ability to learn. So it can change besides just the error. The one that's not related at all is the favorite number and the age. I don't see any reason for it to be related unless there are just some people who choose their age as their favorite number, but I don't know anybody like that. So that one should be close to 0. So things which are not related. I could have also put on there the height of a ball and the time after which it was thrown, because that also will have an approximately 0 relationship because it's quadratic. So then we're left with the 0.65, the negative 0.4, and the negative 0.8. Of the ones left, cigarettes per day, the more cigarettes you smoke, the more likely you are to die younger, right? So it seems that should at least be negatively related. It won't be perfect. I know people, who've smoked a lot of cigarettes for a long time and lived to be quite old, and people who died quite young who didn't. But it should be related, but it should be negative. So that's I'm guessing it at negative 0.4, which is a kind of, weak relationship or moderate depending on your text, but a relationship nonetheless. Height and weight should be a positive relationship, which leaves us with the 0.65. And that may or may not be accurate. What I've done in the past, people aren't keen on telling their weight. So what I've done when I've taught statistics in the past is I'll take a survey and get their height and their same-sex parents' height, so that it's relating height of the child to height of the parent. And that has really about a 0.65, 0.7. It's not particularly strong, but it's decent. So that's what I was using. Gas mileage and money spent on gas probably is not all the way to negative 0.8. It's probably more like negative 0.7 because people drive different distances. And if people drive a huge distance, they may be more likely to buy a fuel-efficient car. And if they drive hardly at all, they'll be more likely to drive a car that is not fuel-efficient because it'll only pay for itself if you drive it plenty. So that has a huge confounding factor going on there. But anyway, this gives you an idea of kind of how to think about this type of thing. So I need to, I think, talk about two other things. R squared, which is the coefficient of determination, I think they're calling it. That tells you the percentage of variation that can be explained by just the linear relationship. So the part that cannot be explained is 100 minus that percentage. So it tells you the amount that can be. So the bigger R squared is, the more it's just this linear relationship. So if you square these, you'll always get something positive and it'll be a percentage. So if, let's say that the IQ thing really was 0.9, then R squared, so we're going from this one, R squared would be 0.9 squared would be 0.81. So 81% of variation in the second one, in this 30-year-old IQ stuff, can be explained by the linear relationship between these two. That means 19% cannot be explained. See, so it works like that. And if you're given R squared instead of R, like you are when you do the ln fit, then you can take the square root of R squared, but you don't know if it's plus or minus R. So you have to know enough about the variables to know if it should be a positive or negative slope. The last thing I want to do is show you how to calculate an R using this formula that they want you to use. So I'm going to just make up some stuff. And in this unit, they are not testing your ability to calculate a standard deviation. That was a previous unit. They will not ask you to calculate all this, including this, okay? So you will be given these two and then asked to calculate this. So let me see. I don't know, maybe I shouldn't write it here because then I won't be able to see it. I'll make it easy. I'm going to use the decimal expansion of pi, so I'll remember that, and 1/7, the repeating part of 1/7. Okay, so now I know what these are. This relationship's going to be horrible. I wonder if I could do it in a different order and get it better. Let's see. That doesn't seem better. That's better. It's not great, but it's better. Okay, so I'm going to use then, I guess, the 5/7 decimal expansion. Okay. So you're going to have to write sum xy equals, and then you're going to have to write 3 times 7 plus 1 times 1 plus 4 times 4 plus 1 times 2 plus 5 times 8 plus 9 times 5. And you have to do the sum of the x's. It's weird. 3 plus 1 plus 4 plus 1 plus 5 plus 9. And you're going to have to do the sum of the y's equals 7 plus 1 plus 4 plus 2 plus 8 plus 5. I wouldn't advise necessarily that you sit and add these or even multiply these, because you're getting a decent chunk of your credit from the thing you enter into Canvas. And if you make a little tiny error here, that won't count against you on the handwork, but it will count against you in Canvas. So I think it's better to be a bit careful. So what I'm going to do is I'm going to go ahead into R, because nobody's telling me I can't, and I'm going to concatenate these things. So I've already written some x, y, and I've already written some x, some y, and I've written out what they are. So if I just suddenly write equals blah, I've still shown my work. So x was pi and y was 5/7. Oh, I forgot to concatenate. Okay, so now I have these two things. So I can write sum x, and hit run instead of enter, and I get 23. So over here now I can just write equals 23. And then sum y, 27. So I can write equals 27. Sum x times y, sum would be better, there we go, is 125. So I can say this equals 125. So I've shown my work and I haven't risked, messing up. So I've got sum xy, sum x, sum y. N is 6, so n minus 1 is 5. And again, you'll be given these SDs. Now, I don't have them, so I'm just going to calculate them here. So you would have been given 2.99 and 2.74. This was SDX, SDY. Okay, so here's the pertinent information. Sum xy is 125. Sum x is 27. Sum y is 23. SDX is 2.99. SDY is 2.74. And the n and the n minus 1. So then we just plug them in. R equals sum xy minus sum x times sum y over n minus 1 times SDX, SDY. And again, you'll be given this formula and you'll be given these two values. So it's just an issue of the sums. Okay, so this is going to be 125 minus, this is, let's see, 621. That's all over 5 times And if you just use these two exactly, I've been told that there's enough error built into the answers that you can use this approximation right here, or use these two values exactly, and that they'll still be fine. So 8.19 And then you can write equals. You don't have to show any more work here. So 125 minus 621 over 6 divided by 5 times 8.19. And of course you'll have it on paper so you won't have to look back and forth at all. 0.525 if I'm asked to 3 and 0.53 if I'm not. So this is the process that you calculate R. So the thing that I would do if I were you is to just make some random lists. Try this yourself using this formula. You can leave this paused and just look right at it. And once you've done these lists, these concatenations, you can do correlation XY. I think that's the right code. What the heck is happening, mouse? Quit being crazy. And see, it's very close. We ended up with 0.525 because I used 2.74 instead of this, 2.99 instead of this, 8.19 instead of this. So we have this, slight difference, but again, it's supposed to be accounted for in the range of values. So if your handwork shows, that you got that tiny amount off for that reason, then I'll get that credit back for you somehow. Okay, so you can check yourself. If these are very, very close and you rounded at points, then you probably did it correctly. There's no reason not to go ahead and check. Okay, it doesn't hurt to make sure that you're not putting in the wrong thing. But then also, if you just try to cheat and do it in R, then your handwork, you'll get no credit, and that's like half as well. So you need to do both. If you watch this before or at studio night, then I'll be here if you want to kind of make some stuff up and see what happens.